Welcome to EDU World Space.
For this problem, for our pool balls, we'll first write down our velocity vectors. So the initial velocity of A is V0. The other pool balls are at rest. So V0 is equal to the magnitude of V0, which is 15 feet per second, multiplied by the cosine of 30 degrees minus sine 30 degrees. So this is actually our direction here, cosine of 30 degrees along the I unit vector minus sine of 30 degrees along the j direction. And the final velocity of VA is along the minus y direction. So it has some magnitude minus VA or VA in the minus j direction. The final velocity of VB is equal to some magnitude VB in the direction sine of 30 degrees I minus cos of 30 degrees j. And finally VC. So all this is coming from our diagram and a little bit of trigonometry, is some magnitude of the velocity VC times the cosine of 30 degrees I plus sine of 30 degrees j. So resolving these vectors into their components, now we need to find VA, VB, and VC, the speed of these pool balls after the collision. So firstly, let's apply the conservation of momentum. This tells us that the initial momentum of the system, which is simply the momentum of pool ball A, m times v0, since the other two balls are at rest, is equal to the final momentum of the system, which is the momentum of the individual pool balls as they move off individually. So mva plus mvb plus mvc. So if we divide this equation by m, we have a common factor m throughout, and resolve into the components. Let's first resolve the I components. We get V0 cos of 30 degrees is equal to VB sine of 30 degrees plus VC, again, cosine 30 degrees. Resolving the J components, remember our vectors VA, VB, and VC, we've already stated above. The J components gives us minus V0 sine of 30 degrees is equal to minus VA minus VB times the cosine of 30 degrees plus VC times the sine of 30 degrees. So what we can do here is we can solve for VB and VC. For VB and for VC. And we get that VB in terms of VC is equal to the square root of 3 over 2 into V0 minus VA. And VC is equal to a half into V0 plus VA. So we have VB and VC in terms of VA. So now we'll apply the conservation of energy. We've applied the conservation of momentum, now we'll apply the conservation of energy. And the conservation of energy tells us that the energy before, which is the kinetic energy due to ball A, a half mv0 squared, is equal to the kinetic energies of each of the pool balls, a half m va squared, assuming that the mass of all these pool balls are the same, plus a half mvb squared plus a half mvc squared. So obviously we can divide both sides by a half m, and we substitute for vb and vc from above, and we're left with the following. We get that v0 squared is equal to va squared plus, and now we'll substitute in for vb and vc from above, plus 3 over 4 into v0 minus va all squared plus 1 over 4 into v0 plus va all squared. So we can see we're left with one equation with one unknown. So v0 squared, we can simplify this, is 2 va squared plus v0 squared minus v0 va. So rearranging this equation, we can see that va, since we know v0, is equal to a half v0. v0 is given as 15 feet per second. So va is in fact 7.5 feet per second. So pool ball A moves off with speed 7.5 feet per second. And now we can easily calculate for VB and VC. So VB is equal to the square root of 3 over 2 into 15 minus 7.5. And hence we get VB, the speed of pool ball B, to be 6.5 feet per second. And finally, the speed of pool ball C is equal to a half, from our equations above, into 15 plus 7.5. And hence we get VC to be 11.25 feet per second.